Physics Notes, Unit 22, Part D. Magnets, magnetic forces on charged particles and wires and magnetic fields. Here we have a loop of wire near a straight wire, and it's another, basically a vector problem. And there's 4 segments in the rectangle. The force between parallel wires, F equals mu 0 over 2 pi I sub 1, I sub 2, L over R. 2 wires with currents in the same direction will attract. 2 wires with currents in opposite directions will repel. One of the difficulties in this problem will be the 2 short segments. But I'll argue that the net force there will be 0. We're looking for the net force. So we can calculate 4 forces here that we have to combine. There's going to be a force on the wire, the 10 centimeter part of the wire closest to the top wire. Top wire has a current of what? 12 amps? 12 amps. And the bottom wire has 18 amps. It's a loop. Well, let's practice the right-hand rule for a little bit. So this segment on the right-hand side has current going this way. So this is current going this way, I. Now the top wire, that straight wire, has a magnetic field that's going to be, in my head I'm thinking this, it's got magnetic field like that. It's called the flux once again. I don't care about that dot up there, but I care about these x's, which get weaker as time goes on, or as distance goes on. But the key is it has a magnetic field. If I put a circle there, that x on that wire, I'm going to erase some of the other stuff. That x that I just drew there on that wire right here, okay, is magnetic field from wire number 1. And I could figure out how strong that is using the equation B equals mu 0 over 2 pi I over R. I don't want to use that right now. The problem here on this wire right here is that force gets weaker and weaker the further away from that wire you get. So it's not a standard force. It's not a constant force. As opposed to the 2 wires that are parallel, they're a constant distance from the straight wire at the top, so that we'll have a uniform force over its entire length. So we can use this equation right here. We can't use this equation right here for those little pieces, the 5 centimeter pieces, because the force is not constant. But I'm just practicing the right-hand rule right now. So that x right there is B. So I'm going to practice the right-hand rule on that little piece of wire there, that little 5 centimeter piece of wire. So my thumb has to point towards the back of the room, towards me. My fingers have to point towards the floor, because x is towards the floor for magnetic field. That leaves a force to the right on that little piece of wire. And that force gets weaker the further we get away from the top wire. So it's not a constant force. It's magnitude F. Anywhere closer to that top wire, it's less than that size. Anywhere further apart, it's more than that size. But if we do this same argument on the other side of this wire, now over here, the current is this way, because the current is clockwise in this loop. So that's the current. The current is that direction. All right, but the magnetic field still will be X. It'll be the same strength at every given distance. So it's going to be the same strength. It's going to vary, but it will have the same strength as on the other 5 centimeter piece of wire over here on the far right. But I'm not going to calculate it yet. I'm not going to calculate it at all, because this is B. If you check out the right-hand rule there, okay, take your right hand with your thumb pointing towards the front of the room and your fingers pointing towards the floor. Thumb pointing towards the front of the room, fingers pointing towards the floor. Your palm faces to the left. So this is really nice. In other words, the force there is to the left. But that force will equal, if we're the same distance from the original wire. I kind of drew these off a little bit, but for every force to the right over here on this piece on the right, the forces to the right, this force is to the left, they will cancel if you're at the same distance. So those will cancel, give you an F net of 0. So those 2 pieces of wire will not contribute to the final answer. So we can ignore those 2 pieces of wire. That's my argument. As opposed to the longer 10 centimeter pieces of wire, those forces will be consistent. I can calculate those using this equation, but the force on this wire will be stronger than the force on the other wire. Even if they're in opposite directions, they won't cancel, because the closer you are, the stronger the force. So I'm going to calculate 2 forces. I'm going to calculate force on the wire. I'm going to switch back to red. I'm going to calculate the force on the wire that's closest to the long straight wire. So the force, I'll call it force 1. Oh, let's just check out the direction as well. Let's check out the direction. So this is an X here. Current is this way. What direction is the force on that wire? Because that's going to be kind of important. The force will be, so, and that's B, there, because the magnetic field is always tangentially towards the floor on this side of that straight 12 amp wire. Once again, all those X's and dots, all the X's right now, are tangential directions to a circle that's circling around that 12 amp wire. But let's see, if I need my fingers pointing towards the floor and my thumb pointing towards the right. So the force on that wire, will be this way. I'm going to call that F1. That's my F1, which I'm calculating right now, far to the right over here. So F1 equals mu 0 over 2 pi I1, which is 12 amps, times 18 amps. Now I take the shorter of the two pieces. I don't know how long the long piece is, but the short piece is 0.10 meters. That's the length of that side of the rectangle. Divided by how far I am, 0.03 meters from the straight wire. So F1 turns out to be 1.44 times 10 to the negative 4th newtons. Okay, let's look at the second wire though. The second wire has current going this way. Okay, magnetic field is still X though. All those X's are from wire, the 12 amp wire, because all of that magnetic field is tangentially towards the floor on this side of that wire. Okay, current going to the left, B towards the floor. So the F is either out and away or in. Let's check it out. Right hand rule. I need my thumb pointing to the left. I need my palm pointing towards the floor. I mean my fingers pointing towards the floor. B field, my fingers pointing towards the floor, thumb towards the left, so my palm points towards the back of the room, or south if you want to call it that. So the force here is this way. Now if F2 was the same size as F1, they would cancel, but F2 is going to be weaker. I'll stay blue. F2 is going to be mu 0 over 2 pi, which you got to plug that in as 2 times 10 to the negative 7th, so that's understood now. That number is 2 times 10 to the negative 7th. Times, let's see, 12 amps times 18 amps, same currents in both wires, but I'm further away. How far away am I? I'm 0.08. That's the, I'm sorry, I got to get the length of the wire first. 0.10 meters in length. Now how far away it is, 0.08 meters. So the force comes out to be 0.54 times 10 to the negative 4th newtons. So I'm keeping them with the same power. It'd be 5.4 times 10 to the negative 5th. It's a much weaker, it's almost 3 times weaker, because almost 3 times further. All right, so now I got to add those two vectors. It's really like subtracting. Take the big one minus the small one. So I'm going to do F net. F net will be the big one, so it'll be F1 minus F2. So that's going to be F1, which is 1.44 minus 0.54. Both of those are times 10 negative 4th. So that's 0.90 times 10 to the negative 4th, which is, okay, that's 9.0 times 10 to the negative 5th newtons. And it's going to be, the net force is toward the 12 amp wire. Toward the 12 amp wire. That's the net force on the loop. All right, so forces on parallel current carrying wires. The Hall effect and the Hall effect probes, the Hall effect equation. Hall effect probes are very sensitive instruments that can measure magnetic fields. You can read the definition here, but they're very useful in motion sensing devices, and like I say, detecting really small magnetic fields. They're useful in fluid flows in pipes, or like fluid flows in blood vessels, like blood in blood vessels. So that's one medical application. Here's the equation. I'm not going to go through the proof of this right now, But the equation is that the potential difference, E, now we're using epsilon for potential difference here, this, EMF, fancy E, equals BLV. We like to use the fancy E there because the V on the other side, the small v, is velocity of the conductor or the velocity of the fluid through the pipe that we're measuring, or the blood vessel. B is the magnetic field strength. L is the length of the conductor or pipe. Let me give you some examples. And this kind of gives you the geometry of it all. Once again, I'm not going to go through all the proof of this and the right-hand rule in regards to this, because it's going to be more just a straight application of the Hall effect equation, which is just E equals BLV. We're assuming everything is perpendicular in all these problems. So just a couple of pretty much straightforward applications. What Hall voltage is produced by 0.210 Tesla field applied across that diameter aorta, blood vessel, if the velocity of the blood is 62 centimeters per second. Well, so that's just going to be epsilon equals, it's just a straight plug-in, 0.210 times the length. Now the length is going to be the diameter, the total diameter, because that's the total length across which it's going to take the measurement. So that's 0.026. So you don't need to take the radius, you take the whole diameter in this case of that pipe, of the vessel, the blood vessel, the aorta here. So I guess that's a pretty good size. I mean, that's an inch. That's an inch. I don't know if that's realistic or not. Maybe I think I made that number too big. But we'll just use that number. That's the number we're going to use. The length, use the diameter, and the velocity, I think this is realistic, 62 centimeters per second. That's 0.62 meters per second. You want meters per second. So you just plug those all in. Bottom line is, well, here, what do we get here? It is 3.4 times 10 to the negative 3 volts, joules per coulomb. I think in the medical application, they have that number, the magnetic field, and the length, and they're trying to figure out the velocity of the blood flow to see if that is a problem for a particular person or a particular situation or part of a blood vessel. That's my guess there. You can do more research on that. All right, what is the speed of a supersonic aircraft? Okay, once again, it's pretty much a straight application of the Hall effect. When you have a conductor, E equals BLV. And once again, they like to use this. I use a capital L. Most of the books do not, but it's easier for me to write a capital L. And we have the voltage. We have 1.60 equals, and we have the Earth's magnetic field. We're using the Earth as the magnetic field through which the airplane conductor is traveling. 8.0 times 10 to the negative fifth. The wingspan of the airplane, it's a long conductor, 17 meters. All right? So what is the speed of this airplane? Bottom line is airplanes get this buildup of potential difference on its wingtips that they have to pay attention to, so there's no electrical problems in the airplane. But let's see what the velocity of this airplane is. And that's 1,200 meters per second. That's almost, it's over Mach 3. 3 times the speed of sound. The speed of sound in standard air is 340. So 3 times the speed of sound is like almost 10 or 1100. This is over Mach 3. Torques on loops in uniform magnetic fields. It's very important in motor design, electric motor design. I'm just going to give you the equation. We're not going to prove it. The torque on a loop or coil of wire, which is one of the main components in motors, along with the batteries, the magnetic field between the two poles of the battery, and then applying current to your loops, I'll show you the diagrams down here, creates magnetic forces that cause rotation of the loop. And the torque can be calculated by that equation right there, where N is the number of turns in your loop, I is the current in your coil of wire, A is the area of the wire, B is the magnetic field strength. So if you increase any of those, you increase the torque, you increase the ability to spin something whether it's wheels of a car or fan blades or so forth. We're going to assume once again that our angle is 90 degrees, which actually it's not always 90 in these cases, but every problem will basically say calculate the maximum torque. Well, the maximum torque is at 90 degrees. One side note, these brushes in an electric motor, basically they're pretty simple. They have magnets, they have a coil of wire, and they have electrical wires that connect everything. But one thing is spinning. We have a spinning coil, but we have wires that are attached to a battery that can't spin. So the way they deal with that is they have these brushes that ride against, and they're not actually like nylon or something like that. They're kind of a soft metal that slide against the turning part of this. This turning part's usually called an armature for an electric motor. And then you have your contacts down here, and there's a gap in there for a reason that we're not going to talk about right now. You don't need to know any of that. It's just kind of interesting how they build these things. And I shouldn't say they perfected the electric motor. The biggest issue with electrical motors is like how good your batteries are. The motor itself is pretty efficient once you get a good battery. Anyway, but what we want to figure out is the torque on a loop. Now, this is different than the one we did in, I think, problem 7 or 8, where we had a flat loop. It was a different geometry than this one. That was just a loop with a straight wire next to a loop of wire. Here's a magnetic field generated by magnets that's perpendicular, in a sense, to the loop. It's going to cause the loop to spin instead of slide. It's going to create a torque. And the more torque, the better kind of motor we have to spin something. Nice thing about this is pretty much going to be straightforward computation. We're just going to get the maximum torque. So it's NIAB sine 90, so we leave that off. In this particular case, they say, okay, torque is 9.5. The maximum torque. It says maximum torque, so that's sine of 90. We have 50 turns. It's pretty obvious what you need to do here. It says, we're looking for B, but we have I. What's the current here? 22 amps. A lot of current. The area. Oh, we got to get the area. So the area here is going to be, it says square. All right, so the area is going to be 0.14 squared. That's the two sides of a square. You figure that out. That's going to go here. And then the B is unknown. Let me calculate this. So the area came out to be 0.020 meters squared. Right, because we had to go in meters, 0.14 meters. All right, plug that in for your area of the loop, one loop. And the magnetic field here doesn't need to be real strong because you got a huge current basically and a fair amount of turns. So that's the uniform magnetic field between the poles of those wires. And the other thing is, like in many motors, there's more than one set of magnets. We're not going to get into all the details of that, but you need a magnetic force, once again, on a length of wire that has current, and all comes into play with all these concepts we've been talking about, the force on a current carrying wire. All right, final concepts here. Magnetic fields in the center of coils and solenoids. Now, what's the difference between a coil and a solenoid? Well, basically a solenoid is a long, thin coil spread out. So this shows you, this diagram right here, the purple or blue is the magnetic field. And the magnetic field is very, very uniform in a long, thin coil of wire. And so we assume it's uniform. Whereas just a coil, which is short and all the wire is basically wrapped on top of itself. And this shows you somebody doing an actual experiment with iron filings. They took a picture of this. There's current in that coil of wire, and they sprinkled iron filings, which are going through the center of that coil, and it's showing you the magnetic field that's generated by the shaping of those iron filings. So that's one example of using iron filings to see a magnetic field. You could do that once again for a bar magnet, like we mentioned, I think way back on the first page of notes, 22 part A. But bottom line, each of these two scenarios has a slightly different equation for the magnetic field based on the geometry you see there. And here are those equations. It essentially takes calculus to prove those. We're not going to prove them. We're just going to use them at face value. A couple things to note. For the coil, the thin, short, big area coil basically, we're talking about the magnetic field at the center of the coil because it's not uniform in that coil. It's the center of the coil. It's mu 0 times the number of loops in the coil times the current in the coil over 2 times the radius of the coil. For a solenoid, it's mu 0 times the number of turns times the current divided by the length of the coil. It's customary to substitute capital N over L for little n. Little n is the number of turns per unit of length. So the equation down here at the bottom is the one you'll see most often for solenoid, but it's the same equation in both cases. The right-hand rule number 1, actually should be right-hand rule number 2. Right-hand rule number 2, according to this book. The number doesn't really matter. Basically, taking your right hand, and if you just curl your fingers in the way that the loops are curled, your thumb will point in the direction of the magnetic field. Like on the one on the right there, if you follow the arrows for the currents, your thumb points in the direction of the magnetic field, which is consistent with those blue or purple lines shown in that diagram. This one here doesn't even have a direction. But once again, if you curl your fingers in the direction that the current is flowing in that loop, your thumb will point in the direction of the magnetic field in the center of that loop. All right, so let's apply this to a couple of problems. Calculate the current needed in a 400 loop per meter. So that's the little n, basically. 400 loops per meter. But I usually don't use that, so I'm using that second equation. So this is for a solenoid. All right, so we're looking for B, which is uniform. Okay, that's mu 0 n I over L. So the numbers here, now mu 0 is 4 pi times 10 to the negative 7th. It's like 12 or 13 times 10 to the negative 7th. Times the number of turns, 400, times I. Oh, we're told B. They told us that B is 1.2. So this is an MRI machine. I think these numbers are pretty accurate. I tried to find fairly accurate numbers. Looking for the current. The current needed to generate this scenario for this. And the length is 1 meter. So it's 400 turns per 1 meter. So that's the N, capital N number of turns over 1 meter. So it'll look like the same equation. It'll be the same equation as this B equals mu 0 Ni. But bottom line is, if you move all the things around, divide both sides by the 4 pi times 10 to the negative 7th, divide both sides by 400, you get a current here in this MRI machine, 2400 amps, which is huge. I'm told that they don't take that much current because they do some other things with iron to increase the efficiency. I'm not sure how, but it doesn't take that much current to generate the MRI magnetic fields necessary to generate the images. But we all know that MRIs are very useful and very important in today's medical technology. All right. Now the magnetic field of a proton, it says, approximately like that of a circular current loop with 1 turn, basically. So it's the other equations. I'm doing these out of order, basically. So this is the B equals mu 0 Ni over 2R. All right, so B equals, and then it's 4 pi times 10 to the negative 7th. This is 1 loop, 1 turn. And then it says the current here, see if I can go down here a little bit. Oh, I'm out of space. The current is what? Oh, it says it's equivalent to 1.05 times 10 to the 4th amps. That's a large current. Divided by 2 times the radius. And the radius is 0.65 times 10 to the negative 15th meters. Small radius. Although those are the standard units, however. So that's just, you go to your calculator and you plug those all in. Turns out that it's going to be a really large magnetic field, 1.0 basically. What? 1.0 times 10 to the 13th Teslas. Huge. All right, so those are magnetic fields in loops and coils. Those problems should be pretty obvious when you get to them. Torques on loops and magnetic fields. That's the nice thing, like I say, about these problems. They're pretty straightforward. All right, the Hall effect. And then there was one practice problem here on the magnetic force on two parallel wires. So that does it for our study of, well, introduction mainly. It's a lot of things to think about for magnets and magnetic fields. And then the next unit, Unit 23, is on electromagnetism, the closer interplay for electricity and magnetism. Although I've kind of stressed a little bit here, and I'll end with this. What is the source of magnetism? It's the movement of electric charges. When electric charges move, electrons and protons, there's a circular magnetic field around that charged particle. Keep that in mind. It's going to be also another important part of the next unit, where we bring a bunch of things together in electromagnetism.